can change here also, right? So this is my talk outline. I'll just with a brief introduction. I'll talk about laser plasma interaction and how this is a new regime compared to MHD, which one is familiar, the audience here may be familiar about. And I'll concentrate in the context of those studies that we have carried out in the context of inertial fast ignition laser fusion scheme, and where the relevance of turbulent electron transport in overdense plasmas become important. So to give a background, I'll essentially summarize earlier studies where I've collaborated with experimental groups at TIFR and ILE Osaka. And we have carried out theoretical as well as simulation studies to explain some of these results. And then I'll come to the recent work which is in progress, and it has uncovered certain interesting aspect of B field generation and turbulence, which needs explanation and understanding. So it's in the just like the theme of this workshop, where turbulence is an open problem. At the moment, it is in progress, and there are certain puzzles, and I'll be happy to discuss that. So as I mentioned earlier, plasma turbulence is familiar in the context of MHD because astrophysical, astrophysics, it appears in the context of astrophysics where the driving mechanisms are slow and happen at ion time scales. And there the electron related, the scale set electrons are introduced in the form of Hall MHD or electron MHD to explain phenomena like fast reconnection or something which happens at a very fast scale. So you are coming from the MHD side to the ion scales to the electron scales because there are certain issues which have to be explained. And whereas I'll be talking of a regime where it is driven at the electron scale, and then in some of the cases, you will see that ion dynamics also becomes important. Sorry. So about a brief introduction about laser plasma interaction. Basically, the laser can propagate inside the plasma only when its frequency is, where is the laser? Yeah. Only when its frequency is higher than the plasma frequency, and otherwise it is, this particular frequency domain is forbidden. So laser doesn't penetrate the plasma if plasma density is higher and plasma frequency is higher in the laser frequency. So we have two particular regimes. The plasma could be overdense or underdense. And if it is overdense, the laser simply interacts with the surface, whereas if it is underdense, it can penetrate the plasma and propagate inside. The laser pulses are typically, the fast femtosecond laser pulses are short, and heavy ions are unable to respond. It's only electrons which gets churned up, and then they drive magnetic turbulence. And in my talk, I'll be restricting to interaction with the overdense plasmas. And the context, as I mentioned, is the fast ignition. What is it? In the laser fusion schemes, if you want to compress the target, basically the objective is to compress the target fuel at a very high density to satisfy the Lawson criteria, NT tau, greater than some number. So where the N is very high. And so one compresses the target, but then you have to heat the target to create an ignition spark. And that means that the plasma there has to be heated at around 10 keV or so. So what one designs is that the laser produces shocks, and these shocks then join, and at the center will create temperature which is about 10 keV, and the fusion burn wave then will keep then burn the entire fuel, and you will get it. But that doesn't happen because the lasers are shining from all sides, and then just like when you pinch something, the pressures where it is not, pressure is not uniform, so the target material just bulges out from there, and then the heating is not concentrated on a spot, but it spreads out, and you need more and more energy to do, which is detrimental to fusion. So that's the conventional example. But in the fast ignition, what one does, compression has been achieved. So you tailor the laser pulses so that the target gets compressed. And once it is compressed, you send a very fast igniter pulse so that it creates a fusion, the ignition spark. So here you can see there is already target has been compressed, and then you are sending an ultra intense laser pulse, which then creates an ignition spark, and then the burn wave is asymmetric. So this is how the fast ignition scheme works. Now the problem here is the target is super solid. So the laser will not penetrate the target. In fact, it dumps its energy to electrons, and the electrons carry the energy and deposit it to ions to create the ignition spark. So electron transport becomes a very, very important issue. And if you look at it, the electron has to interact with the ions. That can happen at collisional time scales. And the Rutherford collision time scale is inversely proportional to the 3/2 of the velocity. V thermal cube. So if you have larger the energy of electrons, the collisional cross sections reduces, and then the classical interaction with ions will be less, and it is likely that the electrons will come and this just pass away from the target without dumping their energy. So it is desirable that turbulence should enhance the resistivity. So turbulent resistivity is here desirable. And in fact, the scale down experiments have confirmed that fusion reaction gets enhanced here. The neutron yields are higher. So something is happening which is stopping the electrons within the target, which otherwise from classical estimates is not possible. So that's why, I mean, one more thing is important, that here we often talk about turbulence as something detrimental, which introduces dissipation, etc. But turbulence provides a facility where you can maneuver things to your liking. And humans, as humans, we always want to maneuver something or everyone, or we want to maneuver even, other humans. So here nature is providing you an opportunity to maneuver things so that you can make, you're not stuck with molecular rates of rates, and then you can improve upon and make things to your liking. Otherwise, one will be stuck at molecular rates, and perhaps even one will not be able to mix sugar in tea while the tea remains hot. So here, turbulence resistivity, as you can see, is desirable. And that needs to be understood. So my work is in this context. And as I've already stated, this is just a repetition that we need to understand the energetic electron transport in the plasma, and what it does as the energetic electrons from the critical surface move towards the target. They moves inside the superdense, overdense target. Then the plasma itself provides for the background return shielding current, and there is a combination of forward and return currents which are unstable. So they are unstable to a variety of instabilities like Weibull, filamentation, two stream, etc. And that leads to the magnetic turbulence, and which may in particular would be enhancing the resistivity. So that's the idea. And it was in fact in the early 2000s that 3D simulations by Sentoku in Japan showed that there is a separation of forward and return currents leading to magnetic sheet formation, and which ultimately through tearing and coalescence instabilities leads to current filament, where the central core carries the forward current, electron current in the target, and the return cylindrical shell, the cylindrical shell carries the return shielding currents, which are ultimately showed because there's a current separation. So at the separation layer, we showed that there will be Kelvin-Helmholtz instability and there will be turbulence there. The experimental evidence that there is indeed a turbulence was provided by an interesting experiment done at TIFR Mumbai, where they had a target in which the laser was incident, the pump beam. It was a pump probe experiment. So the pump beam created a plasma and then created energetic electrons, and then it was probed. That particular area was probed by a higher harmonic laser pulse, and basically it went deeper inside the target to its particular critical density and then returned. So it integrated the region from the critical density of the pump beam to beyond some certain distance, and the integrated information was sent back. And from the ellipticity, there was no Faraday rotation, which implied that there is no axial magnetic field. There was only ellipticity in the scattered laser beam. And from that, they could reconstruct the average magnetic field, which the laser was probing at. And that seemed to grow over picoseconds time scale, 2 picosecond onwards, and then decay like this, which we were able to model by simple only 3 parameters, S0, T0, and tau. This was the source, which is creating magnetic field, and this is the dissipation. And when one estimated this tau value by this fit, it was found that it corresponded to a value of resistivity, which was about an order of magnitude higher than what conventional values would predict. So tau essentially provided an estimate of resistivity, and which was found to be anomalously large. So this was first evidence that something is happening which is making resistivity larger. The next experiment was also very interesting, where it was this was the target, like a fusion target, and from inside the gold, it was compressed by a compressional laser, and then with various timings, the ultra intense laser was sent. Some of the electrons which passed through the overdense core were measured by 20-degree electron spectrometer, and others by 40-degree electron spectrometer. And it was observed that while nothing changed from the 40 degrees, the electron spectrometer kept at 40 degrees, which measured electron which passed only through the corona region, not the dense core plasma. The 20-degree spectrometer showed that if the timing was correct, almost about 15 MeV electrons were also stopped. So this, which is from conventional values of resistivity, this would not happen in a target which is of the size of 10 microns or so. So this was another evidence, and which we could explain theoretically exactly that if you have a density and homogeneity, which was indeed at the interface of corona and the compressed target, then that drives certain kind of shocks, and the mechanism of the dissipation of electron energy was independent of the mechanism. It had a particular value, shock dissipation and ensuing turbulence. And we were able to quantitatively predict that about 15 MeV, it will also stop about 15 MeV electrons. So this was another evidence that there is a possibility of turbulence. And then, it would be better if I'm hurrying it up because I have a very hard bound on time. So I'm trying to speak fast, and so I'm getting a little tired also. And so for turbulence, you should also see spatial and temporal fluctuation should be there. So the experiments at TIFR improved, and they carried out polarigram measurements which could map out the transverse spatial profile of the magnetic fields. And this was what was observed, that the magnetic field were quite random. This is the transverse profile, so integrated over the longitudinal range. And the spectrum, the transverse spectrum was also studied, and it showed although the range of scales, the K scale is small, but this is of enormous number of data, and they consistently kept showing the scaling. The slope was near about -2, which is typically the scale of EMHD turbulence that that people have theoretically talked about, and in some regimes. Now, this spectra was also looked at later times, and while this was the slope, after 17 picosecond also, you would start seeing appearing, there's a kink which starts appearing, and you can see a kink appear at the spectral scale, which at later times. And this was measured with a probe of even higher harmonic, like third harmonic. So the data was very accurate here, and this was carried. TIFR. Yes. The same set of experiments. And this was published here, and how we understood it is that the spectral kink seemed to come up at ion magnetization time scales, and the estimates were made. If you look at the ion gyro period for this particular target, the values were such that they were greater than 12 picosecond, and it started showing up at around 17 picosecond. And if we've looked at the ion gyro radius, which was of the order of micrometer, and kink also occurs at 0.5 micrometer inverse. So it is occurring at the gyro scale. So now the spectrum has evolved from electron dynamics dominated regime to the ion dynamics dominated regime. And it separates, the kink basically separates the MHD fluid when ion kinetic wave alpha regime, because this is the ion gyro radius scale where the kink appears. So longer times, you can see that the turbulence has evolved from one particular species to another particular species, but now from the reverse side. Typically, MHD people look for anomalies of electron scale appearing at shorter and shorter scales to explain faster reconnection and other things. Here, on the other hand, it is going towards the longer scales and hitting the ion time scale phenomena. And the scalings, if you look at it, although we are not very precise with the numbers, but if you see the scales were shallower above and steeper here. And as per Boldrev et al., the cow regime has a scaling of -7/3 or 8/3, -8, which is steeper than -2, as observed in the evolution. And at longer MHD scale, it was shallower than -2. The theories say -5/3 or -3/2, which are both shallower, and that also has been observed. So we have, in fact, the experiments have illustrated that we see an evolution of turbulence. We had talked about anisotropy, inhomogeneity turbulence, and this, in fact, these set of experiments and analysis suggests that we have an evolution of turbulence, and there is a transition or mediation of turbulence from one particular species to other. Now let's look at the power spectra again. The power spectra is high at long scales right from the very beginning, every plot that you show. But if we rely on the instabilities like Weibull, filamentation, etc., then the instabilities pump power at electron skin depth. In theoretical simulation, when you start interpenetrating beams and simulate that, and they get Weibull separated, the scales that form are around skin depth. So the power peaks initially at electron skin depth, but that doesn't show up in experiments. So there is something else which is happening. And what is it that needs to be understood? So this was a movie where I will not be showing it anyway, where you could see that the Weibull destabilization occurs at the electron skin depth. And so there is a clear deviation from conventional understanding about Weibull being the cause of that. And it's only ultimately the coalescence lead to long scale generation. We see longer scales at the very beginning. So we need to address this puzzle. There are obvious differences between experiments and simulations that had been done by that time. Simulations were of periodic boundary condition, whereas laser has a finite spot size. There's no current in the system, no unbalanced current in the system. It was complete balance between the forward and return electrons, current flowing. Whereas if in experiments, I mean, once the forward electron goes, it would take some time for the current to match and basically go to zero. And there's a non-divergent current, homogeneous density was taken, beam could be divergence, there could be density and homogeneity. But the question is, which of these differences are crucial? So we carried out some simulations. We took a bounded beam and the transverse dimension only over these regimes. Again, Weibull instability showed up, and the peak of power spectrum occurred at electron skin depth. But if we choose a slight current imbalance, then something entirely different happened. There was radiation from the edge which went out, and there was a magnetic field which has a transverse scale of the spot size which appeared. And then it's only at later stage that the Weibull and the Kelvin-Helmholtz appeared. And the spectra was also at little earlier times, you got highest power at the focal spot scale length. The evolution of magnetic field was faster because in this case, the sudden jump, it saturates also at a higher level compared to earlier cases where the magnetic energy evolution is very slow. So in this case, the finite current imbalance was chosen, and this is the result we got. This is detailed PIC simulation results where we show this particular phenomena. This is a 3D simulation, and the cut has been taken. So this is the way first magnetic field appear at the edges, and then you will see these Kelvin-Helmholtz instabilities and the Weibull thing here also. In density also, you can see the Weibull, etc. appearing. This is the magnified zoom plot. These are the Kelvin vortices which form. So they all occur at the later stage. This is the 3D picture of the same runs. This was a movie, unfortunately, I cannot show it. And then, so basically it is a finite J that we are choosing, just changes the scenario of the evolution. The other concerns were also addressed. What kind of beam profile should you have? Very sharp, shallow, etc. The size of the focal spot. We are not taking laser dynamics into consideration. It is the electron beam that is the balancing here. So those were changed, and all led to the same kind of behavior. In fact, at earlier, very high power, there was a sudden drop, and this picked up at only later time scales. There was a radiation which was emitted. So this is a plot of time versus this is the beam width and how magnetic field. And these are basically the slope at the vacuum region matches with the C. So electromagnetic radiations are sent out. This is the beam. This is unperturbed plasma, and this is the vacuum region. So the radiation has been emitted. It can be clearly identified. The frequency was plasma frequency and higher harmonics. And so this is what I have already explained. So how do we understand it? The streaming flows, in fact, have free energy sources. and they are unstable to excitation. The modes that get excited are essentially negative energy modes. And in fact, it appears to us that the radiation provides the necessary dissipation. So we carried out an approximate theoretical analysis, which also seems to confirm that, but this has a lot of approximations, but it identifies the characteristic features of the new effect. And let me show that. So this is we took 3 regions, and then we took the equilibrium current zero charge neutral system. So basically there's a finite current which is not influencing the particle dynamics in any way. So this is one approximation. And then we evaluated all the equations and perturbed only the change in the y direction was ky was chosen to be finite, because that was what we saw in the PIC simulation happening. These 3 parameters were chosen to be perturbed parameters, and this is the x-axis, this is y, and this is z. So they were chosen to be finite. And then when we did the linearized analysis of the continuity, momentum, and Maxwell's equation, we got these set of equations, which are 10 variables and 10 equations. They were eliminated. We eliminated all the variables in terms of E1x, and we got this particular equation. This is our main equation. These are the constant equilibrium constants, and F2 and G2 are like this. So if we take a purely growing mode, omega square will be minus gamma square. This is not correct because radiation is being emitted. But suppose we take, and the radiation Mach number you compare with the sound speed, right? Here, I mean, it's a cold plasma, just the propagation. It was a relativistic fluid. Okay. So if we multiply by even x in this integral, then we will get, there will be a boundary term, and then there is this particular term. So this boundary term essentially talks about the radiation. And so if there is periodic boundary, this term will be absent. And then there should be, for even x to be finite, this should be F2 and G2 have to be in such a, the sign should be such that they balance each other. So that can happen if this term S4, which was proportional to current, in fact dominates over this, and this has a negative sign and this has a positive sign, and they balance each other. So for balancing, you should have shorter structures here. If F2 is very small, you will require that the derivatives are higher. Whereas on this particular case, if you permit the radiation to go out, that even with the same sign of F2G2, F2 here is positive, negative terms, this can be hoped to balance these 2 terms. And in this case, the best thing would be that E1 prime, the gradients are very small. The longest scale would be helpful to destabilize the equations. So these boundary terms, in fact, just reverse the physics. And this needs to be improved furthermore. And the calculations are just showing the effect. And so basically, the first term of the flux here contributes to the dissipation and aids to the destabilization process. Now, we also did something that, I mean, like this was a configuration where the forward and return currents were exactly, I mean, they're coming from the opposite sides. But basically, the laser induces a current from here. So we just took an initial condition where there's an input beam current from here, and plasma has to do all the rest of the process. In this case, interestingly, so it captures the very initial stage of the evolution. What we observed that the power was at very high scale, and there was a certain dip at the center near the skin depth. It was empty. Now, can it be measured in the experiment? That was the question. What was being done earlier is that one was sending a pump beam from this side and the probe beam also from this side. So it was capturing integrated regime which was already disturbed. And so it was integrating up to the critical density of the probe beam, which was already disturbed by the beam. So it had a very straightforward power law spectra. But the change of the configuration by sending the pump from here and probe for here, you would just measure the tip of the beam as it digs its hole in the plasma, because that in the experiment, the electron beam itself ionizes the plasma ahead of it, and then all these dynamics happens. So if you, so they, in the experiment, they send the probe beam from the backside. Now it is probing at T1, let's say it will go up to here and probe this particular region. As the beam has evolved, T2, it will probe this particular region, which is again, it's a freshly created plasma and fresh initial stage of the instability. So they also observed, I mean, you should, this green line is not, I mean, it's, the experiment scales, they are reliable only up to here. Green line can be ignored. So you see the power is at higher values, long scale in, and they also observe a dip. So this, which is very much like the theoretical case that we observe. So essentially, our observations show that there are distinct phases of evolution. There's a long transverse scale of beam magnetic field generation at radiation time scales. And then after that, only the KH instability at the edge and Weibull in the bulk occurs. And this explains the experimentally observed spectra at long transverse scales, which was earlier not very clear. And in fact, now we have the experiments are also measuring very initial stages, which matches with the simulation thing. And so radiative losses essentially are acting as a dissipative coupling for the excitation of this instability. And so finally, this provides for an understanding of faster mechanism of long scale magnetic field generation. Counter streaming, as I said, it's a negative energy modes, and it then brought my interest to analogy with the fundamental modes of a star whose instabilities are driven by dissipation of gravitation, by gravitational radiation. These are some neutron star or accretion disk, where this Chandrasekhar-Friedman-Schutz mechanism says that the gravitational radiation leads to a fundamental modes of a rotating star, and it drives certain instabilities. And I was wondering whether this is a electromagnetic counterpart of that, where the electromagnetic radiation leads to the certain kind of instabilities in the system. Thank you very much.
Oh, 2 questions. Yes, please.
What are these negative energy modes?
See, the beam, when it is flowing, it has a lot of it's like a free energy source.
Yes.
So if you perturb a beam, yes, then basically if you extract energy from it, the perturbed state is of a lower energy than that.
Another questions? Yes.
In the last spectra you showed, what are the units? So where is the ion skin depth in?
No, this ion skin depth is not.
Or the Shiro radius.
This is K equal to 1. Okay. So around this region only we will have something like electron skin depths and so on.
Okay.
These are very early time scales where ion have not been perturbed. And early in the sense that you are probing it from this side. So it always remains early.
Okay, then we'd like to thank the speaker again.